Okay, so today we are learning another way to find delta H, and it's the Flippy Thang, and it's short and it's easy, and I actually think it's a lot of fun because it reminds me of a puzzle. And get to the slide that is after the calorimetry, which starts with enthalpy of formation. I'll get there someday. There. Enthalpies of formation. So, some of you picked up this, which you didn't need to. You flinched. I hit Peter and he flinched. I'll talk about this here in a minute, so you can just hold on to it. But basically, you guys need to really know what an enthalpy of formation is. This definition is crucial for thermochemistry, and it's not very hard, even though it looks scary because the words look big. But enthalpy of formation is the heat associated with forming substances from their elements, basically. Okay? So every substance in the whole wide world either releases energy or requires energy to be formed, or it releases energy when it is formed from the free elements in nature. Okay? On this sheet, and those of you at home, I'm holding up the thermodynamic table. This reference sheet is something you might need to use for your homework or whatnot. You will find this thermotable on the website. It says thermotables, and it's a PDF document that you can download if you need anything. There's also thermotables in the back of your textbook. The reason we're using it this unit is because this very first column are all enthalpies of formation. Every single one of these compounds either releases or requires heat to be formed. Think about elements in nature that are already in nature. What do you think their enthalpy of formation is? 0. Exactly. So if you've got something like iron or argon, enthalpy of formation is 0. Think about something like oxygen. How does oxygen exist in nature? O2. So O2 has an enthalpy of formation of 0, but O, that's a radical, that doesn't have a 0. So it's only the elements that exist free in nature that have enthalpy of formations of 0. You need to know that because when I give you little tables on the tests or quizzes, I'm not going to put in the zeros. I'm not going to say O2, delta H is 0. I'm going to assume you know that. Okay? Got it? So what's important about these enthalpy of formations is that they are the formation of 1 mole of a substance. Okay, so let's practice writing a reaction for an enthalpy of formation. Let's say I want to form glucose. And I want to write an enthalpy of formation at standard conditions. Everything I just said. The F is for formation. The little knot symbol is for standard conditions, and I'll tell you what those are in a second. An enthalpy of formation means forming 1 mole of any substance from its elements. So what elements form glucose? Carbon and hydrogen and oxygen. So since I'm forming only 1 mole, I have to keep a 1 there. And so I put a 6 here, a 6 here, and a 3 there. The thing you need to be careful of with enthalpies of formation, sometimes it leads to fractional coefficients in these reactions. Let's pretend I want to form water. Because it's defined as an enthalpy of formation, it has to be forming 1 mole of water. So what 2 elements do I add to make water? H2 and O2. In order to balance this heat of formation equation, I have to leave this as 1 because that's the definition. What do I put in front of hydrogen? 1. What do I put in front of oxygen? 1/2. It is in thermo in this case that we're allowed to have fractional coefficients. Okay? Yes? No, I'm just doing it. I'm just putting the 1 in front of the H to make a point. But no, you're not required to put a 1 there. Now, this whole little not standard condition thing, our standard conditions in thermo are different than they are in gas laws. Gas laws was the exception to standard conditions. And everything else in chemistry, 1 atm is a standard condition. 25 degrees Celsius or 298 K is our standard condition. If we need to be talking about solutions, that we want formations of solutions, the molarity of those solutions have to be 1 molar. So those are standard conditions for anything in thermo. And they're indicated by that little bitty circle up here. So again, heats of formation can be found on a table. But if I were a really nasty teacher, I could make you take every single compound on this table and write an equation. And the number that's associated with that equation is what's on this chart. How much energy is released or absorbed of this equation can be found under the first column on the chart. Got it? Okay. Another thing we need to know, and I'll show you how to apply. Oh, wait. Let me go back. This right here are just examples of heats of formation. Enthalpies of formation examples. So notice we're forming 1 mole of that from its elements, 1 mole of that from its elements. I want to point this one out because a lot of students, when they see this and they want to form a mole of that, for some reason want to make it breaking up into their polyatomics and write Mg plus 2 plus CO3 minus 2. We're not dissolving. We're forming the compound from its elements. So we're adding a magnesium to a carbon and to 3/2 oxygen to make 1 mole of it, okay? So really be careful if I ask you to write a formation equation. Another type of equation you need to write is an enthalpy of combustion. This is so simple. This is an equation or a reaction where you are combusting 1 mole of a substance. That's it. The way it's indicated, heat of combustion. When you see heat of combustion, that's standard heat of combustion. When you see that, they're talking about combusting 1 mole. Just like forming 1 mole, we're going to combust 1 mole. So anybody, pick a hydrocarbon, I don't care what, and we're going to combust it. And we're going to write a heat of combustion reaction. Huh? Glucose is not what I want to do. We just did, well, I guess we could combust glucose. I'd rather do like an alcohol or an, ethanol, and I heard propane. We'll do ethanol and then we'll do propane. Ethanol is C2H5O2, and then propane is C5 what? Oh, prop. God, I'm tired. Propane is C3 what? H8. So we're going to combust these. For them to be true combustion definitions, we need to combust just 1 mole of them. So that 1 has to stay there. And so we make CO2 and H2O in both cases. And then we're going to balance this. So here we have 2 C's, 2 C's. Here we have 5 H's. Oh, I forgot. It's not O2. Guys, you need to stop me from being stupid. That's an alcohol. There we go. 6 H's, 6 H's. And so I have 7 O's and then 3 O's. So I put a 3 here. That gives me 7 O's. Right? All right, to balance this, I need a 3 there. How many H's? How many waters? 4. And that gives me 10 10 oxygens, right? Yes? Wake up, everybody. So I put a 5 there. So these are examples of combustion equations. Again, if I ended up having to have coefficients that were fractional, that would be okay. Yes, Elsa? Because I wrote the original formula wrong. I changed this. Because what do you do when you write a combustion equation? You're adding O2. It's by definition blowing it up with oxygen. I'll show you how we'll use it in a second. Because now we're going to learn the Flippy thing. So this is our third way to find the heat of a reaction. The first way we learned was using stoichiometry, right? The second way we learned to find delta H was using What did we do yesterday? In what? MCAT, but what was the procedure? Calorimetry was a procedure. Here we're going to kind of start to utilize Hess's law and look at how we can manipulate formation equations to get the heat of an overall reaction. So one thing I want to do, when I transferred over to Mac, I lost a lot of stuff, so this needs to be balanced. So I need to put a half here, and I also need to put a half here. My problem doesn't work if the stuff's not balanced. So in this problem, we are supposed to find the delta H for this reaction. Right here, this is the reaction we're finding the delta H for, so I call it the goal equation. That is our goal. We're going to manipulate both of these equations up top in order to get our goal. We can flip them, we can add them, we can multiply through by coefficients, we can do all sorts of things to them, but whatever we do, we need to end up with the goal. What kind of equations are both of those? Not combustion, well, combustion, yeah, but more specifically, we're forming what? 1 mole. So these are actually heat of formation equations. So if I were to look at the chart, if I were to look up carbon monoxide on the table, it would have this number next to it, because this is the forming of 1 mole of carbon monoxide. And this is carbon dioxide's heat of formation equation. I'm also going to be more consistent with units, so we'll make these per mole. All right, so in order to get our goal, we manipulate these two equations. I have a system that I do this. You can do it however you want, but what I like to do, I just start with the first equation they give me. And I ask the question, what does that first equation have that my goal has that the other equation doesn't provide? What is it the sole source of that I need my goal? Carbon monoxide, right? Does everyone see that? Now the carbon monoxide in the goal equation is on the reactant side. There it's in the product side. So what do you think I should do to that top equation? I'm going to change the direction. I'm going to flip it, and I'm going to get this. I have to bring down the corresponding delta H. Since I flipped the equation, what do I do to the number? Change the sign. Don't say flip the number, because that could mean reciprocal. And when we get to equilibrium, we actually do the reciprocal. So change the sign. Yes? Yeah, I just missed it. All right. So we flip the equation, and we change the sign. All right, next. This next one's pretty easy. What is this the sole source of, this second equation that we need? Carbon dioxide. There's one on the product side. We have one here. So we're just going to rewrite it. When you rewrite, keep your arrows lined up. It helps. And then we left that alone. So we're going to leave the number alone. All right. Now to add these, we can cancel stuff out. We're going to have to clean house, get things that are the same out of both sides. What can we cancel? Carbon goes. We can also clean house. If we get rid of 1/2 O2, that leaves us a half on that side. So we get CO plus 1/2 O2 makes CO2. Is that our goal? Yep, that's our goal. So now, because we added those equations up, we can now just add our numbers up. And those will be the delta H. That will be the delta H of our overall reaction, which 283 kilojoules per mole. And that is our heat of reaction for this bad boy. There are a bunch of ways we could come up with this number. This just so happens to be the way they want us to do it. How did we know we need to do the Flippy thing? What did they give you? Equations. When they give you equations, they want you to use the Flippy thing. It's going to be very clear how you need to do it. Tomorrow we're going to learn Big Mama, and technically if I had a thermo table, I could just do the thermo table and do Big Mama on this guy, but that's not how they want you to do it. All right, let's look at the next problem, and it's actually our last problem of the day. And I want to know what the big difference is between this one and the last one. So using the following standard enthalpy of reaction data, if you notice, you see how all of these are forming 1 mole of substances from all the elements? So these are also heat of formation equations. Change these all to mole for consistency. And these are all heats of formation. We don't have to do the F's. I just want you to start recognizing when something is a heat of formation. Okay? All right, we're going to have to manipulate those. And then it says calculate the heat of the reaction for the combustion of 1 mole of ethane. What's the main difference between this problem and that problem? You have to write an equation. What don't we have? A goal. We don't have a goal equation. We have a description of a goal, so we need to write out the equation. This is why you need to know how to write out combustion equations as well. Calculate the heat of the reaction for combustion of 1 mole of ethane. And that's what we're going to do. We're going to combust 1 mole of ethane. Since it's telling us 1 mole, you better put a 1 right there, and you're going to leave it as a 1. So we're going to get CO2 plus H2O. I need 6 H's. I need 2 C's. Ooh, but I need 7 O's. What do I do? I can't times by 2. Why can't I times by 2? We have to combust 1 mole. So I'm going to put what here? 7 halves. This is where the fractions are going to end up being necessary at times. Okay? We got to combust just 1 mole. All right, so now we have our goal, and now we can manipulate all the equations. I, again, just out of practice, start with the first one. Looking at the first equation, what is it the sole source of? The ethane, right? So if you notice, ethane is on the product side. I need it on the reactant side, so I'm going to flip it. And I'm going to get C2H6 gives me 2C plus 3H2, and then I'm going to change the sign on this. 0.68 kilojoules per mole. All right. My second equation, what is it the sole source of? CO2. But what's different? I've got 1 CO2 here, but I've got 2 there. So what do I need to do? Exactly. I'm going to multiply that whole equation by 2, keeping my arrows lined up. So then I multiply negative 394 by 2. And what do I get when I do 394 by 2? 788, negative, I don't know, I just did that in my head, negative 788 kilojoules per mole. Okay, the last one, what is it the sole source of? H2O, and I need 3 of them, right? So I'm going to multiply by 3. I get 3 H2O. Sometimes you have to flip and multiply, so just be careful. Pay attention. 3 halves O2. It is such a cool feeling if you add these up and you get the goal, you're like, yes. It's really cool because it's an internal check. If you add them up and you don't get the goal, you messed up somewhere. So there's no reason to ever miss one of these problems. What do we get when we multiply 286 by 3? What? Come on, calculators. There's 20 of you, 5 in here, huh? 858. Times 3, 858 kilojoules per mole. Okay, so before we actually add those numbers up and assume it works, we have to check that all this stuff cancels and we actually make our goal. So what cancels? The 2 C's, 3 H2s. So looking at this, I'm going to have to combine these. Isn't 2, if we're going to add the fractions, we need 4 over 2, right? So 4 over 2 plus 3 over 2 is 7 over 2. Huh, isn't that awesome? So our ethane is still here, and then we have 2 CO2s, 3 H2Os. Does that match the goal? Yes, it does. It is awesome. And then when I get my delta H of reaction, I add all these babies up, and I'm going to get a negative. So if we follow, and I didn't really do it in the last problem, but if we're following significant digits, we're rounding to no decimal places because this is an addition, correct? So give me a number rounded to no decimal places. It's got to have the right magnitude. It can't be negative 15. Guys, come on. Can we please get our calculators out? Really? Please. We could have been done already. Come on. Negative 1,560? 61. And that's the correct rounding because we're rounding to no decimal places. So that would be the number. And then what are the units on this? Kilojoules per mole. And when we say the per mole here, we're talking about per mole of that whole reaction. 1 mole of the reaction will give us that. And that is the Flippy Thang. And tomorrow we do Big Mama, and we're done with the unit. So it's crucial that you do the homework and practice this, because doing only 2 problems like this isn't going to be sufficient. You need to do some of this stuff on your own. All right. A little bit of study time for the quiz now.